Okay. So we're going to be talking a little bit about chemistry. So we're placing chemistry foundation. And then we're going to start moving into tissues and things like that. So we have to start off first of all with the nuts and bolts. And so in starting off with those nuts and bolts, we're kind of laying some of the groundwork for where biology is kind of founded on. And so when you take a look at it, you're looking at basically the rules of the road, starting off from the beginning portions. So we're looking at, first of all, atoms. We're going to be starting off at sort of that beginning component with the basic building blocks of life. And so that kind of gets us to the idea of matter. And so the important thing about matter is that basically matter is defined as anything that has mass or anything that takes up space, essentially anything that has volume, including us, and that's living and non-living. So pretty much everything in the universe is made up of matter. And there's a couple of ways that you can describe matter. So the first way that you can describe matter is with elements. And so when you take a look at elements, this is kind of like the building blocks. This is the stuff of the universe by which you're allowed to be able to build things with. And that stuff of the universe is given up here on the periodic table. So the periodic table is essentially our list of all the naturally occurring elements that we see, and some of them are manufactured. But ultimately, this is a form of matter. It's a pure substance, which pretty much means there's nothing else in it with the exception of just that thing, right? So for instance, if you take a look at elemental gold, which is a U, then that means that there's nothing in that sample other than just gold. It's pure gold. There's no alloys. There's no anything else. And so we oftentimes will refer to it as any kind of a substance that can be broken down into any other chemical substance, right? So for instance, if you were to take a look at water, water is basically 2 parts hydrogen, 1 part oxygen. So there's 2 different things that goes into water. That's why it's not an element. But hydrogen is a whole an element. There's nothing else in hydrogen except for hydrogen. So that's what makes it an element. And so the important thing about that is when we take a look at the elements that we have in the universe, it's essentially what we have to work with. It's kind of like the artist's palette, so to speak, of what we have to work with to build things. And generally speaking, they come in 3 main phases for the most part, technically 4. But elements can either be found in the universe in their solid state, either in their gas state. So solid state, for instance, for water would be ice, right? Or it can be a gas state like steam, or it could be a liquid state, which is basically what we drink, right? We can also have plasma, but nothing biologically relevant that we work with is in the plasma state. So it's all liquid, solid, gas, okay, and to varying degrees. And so when you take a look at the human body isn't made up of all 92 naturally occurring elements. It's only actually mostly composed of 4. Matter of fact, carbon, hydrogen, oxygen, nitrogen makes north of 96% of all the atoms that are in your body. So you are overwhelmingly made out of these 4. And then there's a smattering of others that are in there that makes up the other 4%. But you are mostly carbon, hydrogen, and oxygen, nitrogen, which what that means is that the majority of the periodic table is not in you. By the way, it's not in any living organism either, right? So all living things have the same kind of matrix. We're all made of the same stuff, the same 96% of CHON. So this is kind of our periodic table. So when you take a look at this, you can see that basically the periodic table is essentially a list of the elements organized by what's called atomic number. And the atomic number basically is the number of protons. We're going to define what a proton is here in just a second. But generally speaking, every entry in the periodic table will have a couple of different features to it. First of all, you have some sort of an elemental symbol in the middle, H for hydrogen, O for oxygen. Underneath it is usually its atomic mass, and that's basically how much this element weighs in nature. So some are diatomic, some are not. And then above it somewhere is what's called the atomic number. That's the number of protons. And simply what we did is we essentially just took a look at all these naturally occurring elements, and we asked how many protons are in them, and we just started arranging them according to their protons. So it's just 1, 2, 3, 4, 5, 6, 7, 8, and so forth. It wasn't really genius, but it turned out to be genius because we realized that those protons actually mimic their chemical behavior, and that turns out to be actually quite significant for us. We didn't know it then, but we know it now. Another way that you can describe matter is with the atom. And the atom we define as the smallest unit of an element. And I would argue it's the smallest unit of matter. What does that mean? That means that this is the smallest that we can get and still retain the properties of the element. So an example of that would be, say, for instance, I always like to do this, right? So if you take kind of a gold, like a gold bar, pure gold, right? Not an alloy, not anything like that, pure gold. It's elemental gold. If you take a look at this, then if you cut this in half, is that upper portion still gold? Sure it is, right? If you cut this in half, is that upper portion still gold? Yeah, it's smaller, right? If I cut this in half, is that square still gold? Yep. If I cut that in half, is that still gold? You get the idea. If I take a smidge, a little pinch, is that little pinch still gold? Now, if I take it down to a single atom, is that atom still gold? It is, right? That's the definition of what we mean by the smallest unit of matter. It's the smallest that you can get and still retain the properties of gold, which is what? Well, what do we know and love about gold? Why is it so valuable to us? Huh? Shiny? Yep. What else? That's luster, right? So that's a physical property of gold. What else? What are the other properties of gold that we like? It is heavy, dense, right? Very dense. What else is intriguing about gold? Yes, that's true, right? So that's a nice one. What else? It's funny, you guys are getting all the hard ones, but you're not getting all the obvious ones. Why do you have a jewelry store and you have gold? It's not because of its antioxidant properties. Although, if that was it, then you're totally in nerd territory. That's why you're jewelry shopping, right? But what's value, right? Because value is relative. We can value anything. If we wanted to value dirt, we could value it and actually get a fight over it when we kill each other over it. So, but value is relative. But what makes it valuable? I'm looking for chemical properties, chemical physical properties that are inherent to the gold. So I got shiny. That's the way it looks, right? So we like that. Dense. Fairly antioxidant. What? It's what? So that would go along with value, right? But so we're just looking at pure gold, so it is real, right? So what is another chemical property of gold? Think obvious. You accessorizers. What color is it? Yeah, it's got its own shade of yellow, right? Its own peculiar sense of yellow. We call it gold. That's another physical trait, right? So that's another one. For those of you who happen to have real gold at home, what is it like to work with? Like if you were a goldsmith? Soft, very soft, right? Which is actually one of the really high values. So what makes it valuable is the fact that it's very soft, right? And it's yellow. It's got an attractive yellow luster, shininess associated with it that we like. It glows at us, almost like the sun. Of course, back in the day, we were sun worshippers and things like that. So gold would be a naturally attractive sort of thing. It's got yellow like the sun. It's soft so that you can work with it. It doesn't corrode like silver, right? It does indeed, right? And so, and none of that, but the other thing that we like about the goldsmiths love about it is, unlike other metals, is since it's soft, you can coat things with it, right? So metal inlay, gold inlay, or gold leaf, right? So oftentimes, if you don't have the monies of an emperor and you want to economize, you can take wood and actually hammer gold into thin foil sheets, and you can cover the wood with it. Basically an old version of gold plating, right? And then you could have temples that were just gleaming in gold, even though underneath they were actually wood. But the gold, because it doesn't react with anything, would protect the wood from oxidation. And so you would essentially have this incredibly brilliant temple to the sun god, so to speak, right? And it would be impressive. The other thing that kind of goes along a little bit with its relative stability is its conductive capacity, right? It's the best conductor out there, actually. Matter of fact, we always think of copper as a conductor, but the copper is like poor man's metal. This is what you do when you're poor. Like most people, like we couldn't afford electronics if they weren't made out of things like copper, because copper is an effective, efficient, but cheap source of conduction. And that's what we make our electronics out of. If we wanted perfect conduction, we would make all of our electronics out of gold. Unfortunately, nobody would be able to afford a laptop. Right? So it's out there. But if you go down to Colorado Springs, have you ever been down to the Space Museum down in Colorado Springs? Oh, shame. Down there, it's awesome because they've got like all of like the old retired equipment from NASA. Like you'll see old satellites in there. You'll see old space suits in there. Like little stories of which astronaut walked around the space station in the suit or whatever. It's really cool because it's like the actual stuff that was actually active in the space program, and they kind of have it all housed there. So, and they got all kinds of stuff. They got, especially the satellites. I love the satellites and the modules. Because one of the things you notice in the satellites, especially if you take a look at like the kind of the video image, they took like the video of it actually working in space itself. They don't have it on the floor anymore. But when it was working in space, one thing you notice is all that yellow gleaming metal all over it. Not the entire thing, but a lot of the electronics, the circuitry is made out of gold. Why? Because when you shoot out a satellite, especially like one of those distant galactic satellites that we just intend to have cruise out there forever, sending us information back, and we just kind of turn it loose, kind of like Viking, for instance, right, which we turned loose in like the late 70s, and it's just still going. We want it to be able to communicate with us, right? We want it to keep sending information back to us. That's how we learned about Pluto, by the way, right? Is we kind of had this information coming back to us from Viking that was still sending information. So how do you do that? By making sure its circuits are incredibly efficient, and the most efficient way to make the circuits is out of gold. So all of these NASA circuits are made out of gold because they're the best conductors out there. Okay. So when it matters, we make it out of gold, and then we just get rid of it. All right. So that's kind of the important thing, right? So now let's go ahead and do something. Now let's do something crazy. Let's blow the atom up into its guts, parts. I ask you the same question. At that point now, is it still gold? No. Just like you're no longer an individual, a functional individual, if I rip your arms off and your legs off and your head off, right? At that point, you're just body parts. So just like the atom is the smallest we can get and still retain the elements of the element, right? The features of the element. So too, if we blow it up, it's no longer a functional unit. It's no like just body parts. It's atomic body parts at that point. So the question is, what exactly are these body parts? Well, before we get to the body parts discussion, we need to make sure we understand and underline one particular thing. That is to say what atoms tend to do. What atoms like to do is they basically like to form associations with each other to form molecules. And I kind of already wrote one of those down, right? For instance, you take an atom of hydrogen with another atom of oxygen, and they can form the HO bond. If you add another hydrogen to that, then you form water. Right, so basically what you have now is you have a molecule, relatively small molecule, but still a molecule. And so this is what atoms do. This is how you build stuff in the universe, right? You basically take these atoms, they form associations with each other, and then those associations will become molecules. And then we kind of build on that idea and that theme, as we'll do that later on in the chapter. But let's take, first of all, look at some of the parts associated with the atom. So if you were to basically take a look at the atom and kind of crack it open a little bit, what you'll notice is basically you're made up of subatomic particles. And so you have three major subatomic particles, and and they're divided up into two regions. So the first region is the nucleus. The second region is the electron cloud. So in the nucleus, you have three major particles. So you have two major particles in the nucleus and one in the cloud. So the first one that we're going to see is what's called the neutron. Charge-wise, it has a neutral charge. Mass-wise, it's very large, and we tend to abbreviate it as N0. So if I were to take a look at this, I basically have these three particles with no charge in them. I'm just going to put a slash through them to denote 0. And so those would be your neutrons. In addition to that, also in the nucleus, you have protons, which are positively charged. These are also large, about the same size as a neutron. They're positively charged, and we tend to abbreviate them as P+. Okay. Now, these guys also you'll have in the nucleus. So you'll have these guys hanging out there. That's your nucleus. Now, around the nucleus in your electron cloud, you have another particle called electrons. So these guys tend to be negatively charged. They're orbiting around the nucleus in what's called electron shells. We'll talk a little bit more about electron shells here in just a second. These guys, size-wise, mass-wise, are vanishingly small. Now, what does that mean? That basically means they're so small, they're literally in danger of winking out of existence. They're so tiny, relatively speaking. And we tend to abbreviate those as E negative. So for instance, here is my electrons. So basically the guys are going to be whizzing around a nucleus in this cloud-like area where the electrons hang out, inhabiting structures that we now refer to as shells. Okay. So let's take a little bit more of kind of an up-close look at that. So if we take a look at our atomic structure, we're going to take a look at hydrogen first, because that is simplest. Hydrogen, if you take a look at it, has a mass of 1, has an atomic number of 1, which basically means it has 1 proton. And since it has a mass of 1, it has no neutrons, because that 1 is the mass of the proton and has 1 electron. So here you can see you've got your 1 proton in your nucleus, and that 1 little electron zipping around the nucleus quite happy like. Now, what we're looking at here is what's called the Bohr model, which is kind of not the way it actually works. Chemistry and physics, we've figured quantum mechanics has sort of changed things a little bit. However, we still use this one schematically to kind of help organize how electrons behave and how to classify them. Generally speaking, you're going to have in hydrogen, you're going to have your 1 proton, which is going to have a mass of 1. We typically use a mass unit called the atomic mass unit, which we define as the mass of 1 unit. Excuse me, mass of 1 proton. So the proton is a relative measure, so that's 1 AMU. Everything else is compared to the proton. It has, in this case, actually, this should be down here. It has no neutrons because it's got a mass of 1, and it's got 1 electron. So those two numbers were flipped around in the PowerPoint. Okay. So that gives you an atomic number of 1 with a mass of 1, right? The size of 1 proton. Now, if you were to take a look at others, basically what you have, so this find here, this little ring, it's like a little galactic ring, so to speak, is basically an electron shell. Generally speaking, this first one we refer to as n equals 1. And in this first one, we have a max possible of 2 electrons that we can put in there. So we have plenty of room in there for hydrogen because there's only got 1 electron. Okay. But what about others? What do we do about others? Let's take a look at carbon, for instance. How many electrons does carbon have? It's got 6 protons. Its mass is 12, which means it has 6 neutrons. 6 plus 6 is 12, right? And then it has 6 electrons. Okay, so first of all, the first shell that we have here, which is n equals 1, has a max of how many? 2 electrons. So 2 of those 6 fills up that first shell. Now we're stuck, right? Because we have 4 more, don't we? So what does that mean? We have to open up another shell. At this point, this is going to be n equals 2. And from here on out, n equals 3, n equals 4, n equals 5, you're going to have a max of 8 electrons. Plenty of room for what carbon has left over. So as a result, it's got 4 electrons in that second shell, but it's also got 4 empty seats that it can fill before it fills up, right? If you take a look at nitrogen, it's the same kind of thing. In n equals 1, you have your 2, and then in the n equals 2 shell, you have 5. So in this particular situation, now you have 3 seats that you could fill, right? So here's 3 left over. And oxygen, which basically means you have 8 electrons. You fill up to 2, you have 6 more that go out into the n equals 2. That leaves you how many? 2 more, right? Before you fill everything up. So here you have 2 left. Okay. So why do we care about that? The reason why we care about that is because these outermost that you see on these outermost shells drive bonding. And as a result, we're interested in those. Not so much the inner ones, outer ones, right? As a matter of fact, because those are the ones that are involved in bonding, we have kind of another way of writing these. That's a little bit, it's called the electron dot diagram. So for carbon, it has in that outer shell 1, 2, 3, 4. In nitrogen, it has 1, 2, 3, 4. Let me put these two over here. 5. I want to erase these 2. So that's how many it has. 1, 2, 3, 4, 5. And oxygen, it has 6 in its outermost. 1, 2, 3, 4, 5, 6. So the number that you have in that outermost shell is what we're interested in. This is referred to as a special name, the valence electrons. Why does that matter? Because carbon can form how many bonds? 4 bonds in each of these little seats that it has open. It's kind of like, how many seats do you have left there for people to sit in? I've got 4. Okay, we'll sit 4 people there. You can sit 4 people there, right? It's kind of like how many openings do you have before you fill yourself up? I've got 4. I can take on four new atoms. I can share with 4 new atoms. I can make associations with 4 new atoms before I'm done, before I'm full, right? So that's kind of what we take a look at. Those outermost electrons are the ones that are the most important because they're the ones that drive bonding from one atom to another. It forces different atoms to associate with each other. Okay, so on the periodic table, we talked a little bit about this, right? So you basically have your atomic number, which if you take a look at an elemental symbol, and I'm going to kind of abbreviate this. So here's my elemental symbol, 1, 2, 3, 4. In position 1, you have your atomic number. Always rewrite our atomic number in that lower position. Remember, this is the number of protons. It's also your atomic ID. That means it's who you are. Now, here's a good example. Here's an example of carbon. How many protons does carbon have? Six. The silent count, right? It's got 6. That's your atomic ID. That's who you are. Why? Because what happens if I add a proton? I go from 6 to 7. Am I still carbon? What am I now? Now you're nitrogen. You're not even the same person anymore, right? If I take a proton away, what are you? Yeah, you're boron now, right? So you're not even the same thing. So this is your atomic ID. As a result, what that means is, typically speaking, atoms do not want to change their ID. What they want to do is they want to be happy who they are. Carbon wants to be a happy carbon. It doesn't want to become nitrogen. It doesn't want to become boron. It wants to stay carbon, and it wants to be happy. as carbon. So generally speaking, most of the time, atoms do not want to change their identity, which means when you're kind of doing all these things, you don't ever change your proton number. Now, in position number 2, this is your mass number. So that's this guy right here. Generally speaking, this is determined by the sum of your protons plus neutrons. Why not electrons? Yeah, right. I said they're vanishingly small, right? So basically, atomic mass is sort of like me saying, how much does a watermelon weigh? You wouldn't make an accounting for the dirt that's on the watermelon, would you? Because it's so tiny that it doesn't have any play or any effect or any addition to the actual weight of the watermelon itself, right? Same thing is true. You don't really care about the electrons because they're literally so tiny that they don't add anything significantly to the overall mass. Now, this is basically just the addition of the protons plus the neutrons. And as a result, what oftentimes you'll see is you'll see numbers written there. Like, for instance, I'll have, say, carbon, which has 6 protons, and I'll have a mass number of 12. Or I'll see something like carbon 6 with a mass of 13, or I'll see carbon 6 with a mass of 14. Now, the reason, so these are all carbon, yes? How do you know? Because they all have 6 protons. But they're not the same type of carbon, are they? So they're what's referred to as isotopes. So isotopes basically are essentially atoms of the same element that have the same number of protons, that is, but they have a different number of neutrons. So for instance, whenever you take a look at these 3 right here, how many neutrons does carbon 12 have? It's got 6, right? 12 minus 6 is 6 neutrons. How many neutrons does carbon 13 have? It's got 7, and carbon 14 is 8. So these are isotopes of each other. They're all carbon, but they are all have different neutrons. Okay. So what that creates then is differences in their mass, but it also creates what's called radioactivity or radioisotopes. These are basically unstable isotopes. They're big and clumsy and unhappy typically. And in order to become happy, what they do is they emit radiation. They basically are trying to stabilize their nucleus. So they got a big clumsy nucleus, and they're trying to bring that down to a more stable size. And the way they do that is by emitting stuff, they're kicking stuff out of the nucleus, literally kicking out things from the nucleus, particles from the nucleus, so they can slim themselves down and become more stable. When they do that, they emit energy in the form of radiation. Now, the radiation can be bad, right? So ultimately, radiation can damage your cells. If it goes after your DNA, it can cause cancer. I'm looking at you, sunbathers. UV radiation mutates your genes, mutates your DNA because you're out there bathing in the sun all day long. And then you're surprised when you get a melanoma diagnosis. That's because you've been bathing in mutation level radiation. Remember that next time you go to Lowe's tanning salon. Right? Basically mutating yourself, giving yourself cancer. So there are also useful, by the way, with radiation, you need to understand the nature of radiation. Usually when we think of radiation, we think of like nuclear bombs, right? That's what we think of. We think of, nuclear reactors. Fukushima, for instance, is the most recent version of a nuclear reactor disaster. Chernobyl, for those of you who know about Chernobyl, that was full-on meltdown, unbridled meltdown. What happens if things go horribly wrong? To this day, that's an entire area of Ukraine that's uninhabitable, unless you want to get like a lifetime dose of radiation within hours. Generally speaking, you can't go there without a lot of permits and a lot of harassment because it's a pretty lethal area. You can't go there and survive at the same time. So that's usually what we think about. But there's radiation everywhere. So we have what's called background radiation. It's all around us all the time. whenever we go outside, just natural radiation, cosmic radiation is coming from the sun. It's just a natural part of being alive. In Colorado, we have natural radiation in the soils. How many of you guys have radon mitigators on your house? Big white tubes with fans on them. They're constantly going. So basically that is, what that's doing is it's taking radon, which is in Colorado soils. And when we build basements with exposed crawl spaces in the basement, what happens is radon is a type of radioactive element. And what it'll do is it'll emit radiation in gas form. And that'll build up in your basement. And so if you've got a finished basement with an unmitigated crawl space in there, then that radioactive gas builds up and it increases your likelihood of getting lung cancer. And so as a result, oftentimes you'll have houses, you can see them, pay attention to it. It's big white tubes. It looks like a chimney sort of on the side of the house. It just vents that radiation. All they do is just take a fan and they just kind of suck, just gently over time. They just kind of suck whatever airspace is on top of that exposed soil, and they just suck it and just release the atmosphere. And it's fine because once it dissipates in the atmosphere, it's not a problem. It's just because it's accumulating in your basement that it becomes a problem for us. So when you go house shopping, pay attention to the basement. It's one of the reasons why when I look at houses, the finished basement is not attractive to me. Okay, because most of the time I take a look at that and I'm like, yeah, you're probably overlooked that, didn't you? There's probably a couple things you did. In order to spiff up the house, you probably ignored flooding hazards and the need to have exposed plumbing and pipes so that you can work on them, especially if it's an older house. So you can't get to that anymore unless you damage your basement during flooding. And the other one is radon mitigation. So I don't see any access here for mitigation of radon. So those are completely neglected. So yeah, that's why I don't houses with finished basements. But not only that, but I mean, that's not a place to live. It's a place to bury the dead bodies. So that hurts me mostly. I knew it. Right. Right. So that's basically what we have. So radiation all around us. And we kind of have to be careful, but we can use it for imaging, right? So for instance, when we take a look at imaging, it looks like PowerPoint's about ready to crash on me. There you go. So for instance, you can take a radioactive iodine or like a radioactive iodine element, and then that'll go to your thyroid. So that's one way that we image your thyroid, is because that's the only really active area for iodine consumption is in the thyroid area, so we can use that. Or we can use different types of radioactive contrast elements and things like for different types of imaging that will help to sort of highlight that particular area of your body. Now, we're not talking about tons. We're not talking about a lifetime exposure of radiation. Like what we did was in cardiology. We do nuclear stress tests, and the patients were always worried about that radiation component of it, which is good. But the amount of radiation you in terms of that radioactive isotope to kind of highlight the blood, to sort of light up the blood so the cameras can hit, it passes through the heart region that's stuck in an artery. You can see that too. Equivalent of about 2 seconds. So we're not talking about a ton of radiation, because what happens is we got very, very sensitive to that illumination, that radioactive emission. Very sensitive to that, so they can see that very, very easily. You don't need a whole lot. And so don't, if you have to go do nuclear imaging, don't like stress out too badly. Certainly ask, what levels of radiation it is, but most nuclear technicians have that right at their fingertips. It's like, yeah, this particular one is about maybe 2 chest x-rays, the amount of about 2 chest x-rays. This one over here, maybe a little bit hotter, right? And this one over here is a little bit cooler. Indeed, it is. Yes, indeed. Now let's see if you can hold it on here. So it looks like Zoom was responding to a network failure that was happening. But our recording is in progress and we can see the screen. Excellent. Okay. So then what happens then once our atoms kind of form associations, right? So we said that basically atoms will form associations. They'll start to form molecules, oxygen, water, things of that nature. And so ultimately then we have two different ideas, right? We have the idea of molecules, which generally speaking are can be made of either the same or of different atoms. And then compounds typically are only made of different atoms. So for instance, H2O is both a compound and a molecule. Oxygen is only a molecule, but not a compound. And in chemistry, they get really picky about this terminology, but it's as simple as that, right? That's the simplest way to think about it. Just typically because it encompasses both same and different atoms, I tend to use molecules. I don't usually tend to use compounds, like the terminology. Anyway, okay. So when these atoms are coming together, they're going to be forming associations with each other, and those associations are going to be in the form of bonds, which typically come in the form of either an ionic bond. We'll take a look at that one here in just a second, or the covalent bond. We'll also take a look at that one as well. Now, when it comes to ionic bonding, generally speaking, in an ionic bond, this is basically when two atoms, and bonding in general, is where two atoms are seeking to take their valence shell, that's that outermost one, right? And they want it to be full. So what drives this is something that we refer to in chemistry as the octet rule. And basically, this is kind of like your drive to be perfect. So for you, atomically, perfection is a full outer shell. And so all the atoms that don't have full outer shells are striving to be perfect by partnering together in order to fill that out. Okay, and that's the motive. That's the motivation for these atoms to come together and to form associations, is to fill that valence shell. Now, in an ionic situation, what happens is typically one atom will donate an electron and the other one will take. It's like a transfer. So in an ionic bond, this is basically a transfer of electrons from one to another. And so then what happens is, because it's a strong transfer, it's like I give it to you, I'll take it from the other. What creates essentially is ions, which are essentially particles that are charged either positively or negatively. Now, if you recall, where I had my little elemental symbol up here with positions 1, 2, 3, and 4, I didn't say anything about 3 and 4 yet, did I? 1 we know is atomic number. Position 2 is the mass. Well, what's 3 and 4? So 3 is basically the charge, there's a G in there, on an ion. So for instance, sodium has a charge of +1. Chlorine has a charge of -1. Okay, so in that third position is where the charge of your ion goes. This is essentially where your number of protons is not equal to the number of electrons. Normally it is. Matter of fact, everything in nature on the periodic table is understood as neutral. That is to say that there's the same number of electrons as protons, unless you're an ion, like if you're involved in an ionic bond because you've transferred an electron, I've taken it, now I've got an extra negative charge, that makes me -1. Okay, and I'm happy that way. That's the idea, right? The point is you're happier after than you are before. In position number 4, you're looking at the number of atoms in a molecule. For instance, C6H12O6. What is that? Glucose. So here you have 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen in one molecule of glucose. Okay, so that's kind of what the other 2 designations give you. And so in this particular case, in an ionic bond, you have a give and take of electrons. So the giver will become positive because they've lost a negative charge. The taker will become negative because they've gained a negative charge. And so they exist as ions or charged particles, and they're happy this way. And that forms this attractive bond between them, the ionic bond. So here's what it looks like. So here's a molecule of sodium. Now notice when you take a look at sodium, it's got 11 electrons. So on the first shell, you have a max of 2, so you fill that one up. You have more, right? Because you got 11, so you got 9 left over. So then you open up the second shell. Here you have a max of 8, so you fill that one up. Got 1 left over, right? So what do? You have to open up a third shell. And this one has still a max of 8, but in this case, you only have 1 electron to fill it. It means you have 7 empty seats. Okay. In chlorine, it's a little bit different. So sodium you could take a look at as having 1 valence electron out there. Remember, we said we're only interested in those outermost. Chlorine, on the other hand, is just the opposite. It's basically got 17 electrons. So it's going to go 2 on the inside, then 8, right? So that's for 10. And it's got 7 more to go on that third shell. But guess what? It's really 1 short, right? And so basically we take a look at chlorine. 1, 2, 3, 4, 5, 6, 7. So it's got that 1 sitting right there. So it's 1 away from being completely full. And so since it's so close, it creates kind of a sense of chemical desperation in the atoms. The closer you are, the more desperate you are. We saw that with the Olympics, right? I mean, literally, if you're really that close to like winning it all, I mean, you're willing to do anything it takes to get there, aren't you? I mean, you'll cut your tongue off and throw it over the finish line just to finish first if that was allowable, right? So the fact that you're so close makes you more desperate. The same thing is true here. The fact that you're so close to having a full shell means you're desperate. Chemically, that means you're kind of a little bit more reactive. You're a little bit more chemically crazy in terms of your temperament. Now, the runners who are kind of a little further back in the pack, they're not quite as desperate, are they? Because they know there's nothing they can do. They're not even going to finish in the top 3, right? For them, they're probably just happy that they're running with some of the best and fastest in the world. So for them, just being at the Olympics, representing their country, is like a big deal. And so they're already done. They're already satisfied. So for them, they're not quite as desperate. And that's kind of like some of these others that are somewhere more toward the middle. Like, for instance, we said carbon had how many valence electrons? 4, right? Right in the middle. It can either lose those 4 or it can gain those 4. But it's like right in the middle. Not super desperate, but still wants to fill out its shell. That reflects in its temperament and its reactivity. So it's not necessarily quite as crazy as, say, for instance, these what's called the halogens, which is fluorine, chlorine, bromine, iodine, and antimony. Right. So those guys are really, really, really reactive, and those typically are the ones driving this sort of ionic bond. It's like, I want your electrons so badly, I'm going to take it, mine, and I'm going to exist as a negative ion, and I'm happy that way. That's me in my happy place. But the other guy is the same way. It's like, I'm really unhappy because I got this extra thing, and it's like it's forcing me to open up this new shell, and I want to get rid of it, because if I get rid of it, I don't have to open up this new shell, right? It's kind of like a waste for me. So here, you take it. I don't want it, right? And now that means I'm going to exist as a positive ion because I lost a negative charge, and now all of a sudden I'm happy. So now I'm in my happiness, but I'm existing in life as a positive ion. Yeah, go ahead. Yeah, so in that case, like for instance, if you have magnesium, right, which basically has 2 electrons. So if you take a look at this one, you can do the same thing, right? So you have magnesium with 2, you have chlorine, who has 7. So in this case, you can share 1 pair of electrons there, right? But guess what? It can do the same thing with another chlorine. So magnesium chloride would be MgCl2. 2 chlorines per magnesium, whereas sodium chloride would only be NaCl. That make sense? So in this case, magnesium has 2 situations, like 2 electrons to deal with. And so it has to make 2 bonds in that particular case, right? So that's kind of, that's one of the things that you can do. So basically, the other thing you notice is I'm using metals, which are these guys over here. So the group 1 are the alkaline metals. Group 2, which is from beryllium going down the family, that's the alkaline earth metals. These are all metals over here. Of course, you have transitional metals. We won't talk about those. That's chemistry. We'll let them worry about that one. And then over here, you have the non-metals. So like, for instance, fluorine, chlorine, bromine, a lot of these are gases. So they're non-metals. Chlorine is a gas, for instance. But these are all non-metals. And so typically an ionic bond is formed between a metal, left side of the periodic table, and a non-metal, right side of the periodic table. That's a pretty typical pattern we see. Now, for sodium chloride, what we also see is since they're existing happily as ions, they stack that way when they form their crystal. For instance, you can see here that your negative chlorine is surrounded by your positive sodiums. And your sodium here is surrounded by your negative chlorine. So basically, it kind of stacks that sort of opposite charge around, which creates this nice little sort of square crystal. And then that's kind of like your little salt crystal. That's what you're basically pouring on your food. That is so incredibly yummy. Okay. Says the mammal. That's one of our instinctual cravings, salt, of the 3 big instinctual cravings. Okay, so that's basically when you just flat out give it away, right? Because you're just so strongly attracted to it or not. The other one is covalent bonding. Now, covalent bonding, instead of a transfer, what's happening is you are sharing electrons. So it's kind of like a custody problem. So you don't just have an outright, I'm just going to give it all away. You have to sort of come up with some sort of a plan, a truce, if you will, an agreement between the 2 atoms that you're going to share these electrons. And so ultimately, they're sharing the electrons for the exact same reason, to basically fill their valence electron shells. Generally speaking, each of the atoms will contribute 1 electron to be shared in the pair. And so that electron then will spend varying amounts of time in each of the shells of both atoms. So I'm going to put that in there, though, varying amounts. Just like the kid will spend varying amounts of time with each parent. But it is variable, isn't it? And the amount of time you spend with one parent versus the other can change quite dramatically depending on the custody agreement between those 2 individuals, right? And so, as it turns out, that custody agreement situation does actually mirror the way atoms share and kind of come up with a plan to share these electrons. Okay. First of all, whenever you're sharing electrons, it is a single bond. That is to say, I'm going to take a look at the two carbons, one single bond. So each bond or each line represents one pair of shared electrons. In a double bond, you have two pairs of shared electrons, and in a triple bond, you have three pairs of shared electrons. And so this is common notation for us. So here's kind of what it looks like. So here's basically an oxygen. You can see that you have basically two valence electrons. So what's going to happen is a hydrogen, which has one, is going to come in and say, listen, I got one, you need one. So why don't we form a relationship here? We're going to share these two electrons in a bond, and that will be an agreement between oxygen and hydrogen to share those electrons. Now, they're happy because hydrogen has filled up its shell because it has a max of 2, right? That first one. So it's happy. Oxygen, if it forms another one with hydrogen, will form and fill up its shell. So now it's got 8. 2, 4, 6, 8. Oxygen is happy now. So is hydrogen. I scratch your back, you scratch mine, right? But only in the context of the bond. So if you break that bond, then you're no longer happy, right? And so that's kind of something always to keep our eye on. In terms of two oxygen molecules, here we can see we have a need for 2. So one oxygen said, hey, guess what? I need 2 as well. So why don't we go ahead and share these 2? That'll create one bond. But guess what? I got another one, and you have another one. So why don't we share this one as well? So that'll create the other bond. So oxygen looks like that. It's a double bond. So a couple other things you can see, however, is that we'll take a look at is polarity. And I want to unpack that one right about here because we have one here. So in terms of covalent bonds, there's 2 different types. There's what's called a polar, and this one is a non-polar. So what does that mean? That basically means you either create a positive or a negative end, or you don't. Now with water, you do. And here's the reason why. Because when you take a look at water, it is a polar molecule. What that means is every atom has an attractiveness toward electrons. It's almost a magnetism, so to speak, for electrons, called electronegativity. And it increases going up the periodic table and over. So it increases going this way and this way. So when you take a look at oxygen, which is way over to the right, versus hydrogen, which is way over to the left, who has the higher attraction toward electrons? So it'd be this one, right? Oxygen. So by a lot. So what that means is when they're in a bond with each other, even though the electrons are in the cloud, what happens is the electrons tend to spend more time over here by oxygen because it is more attractive. It's like it sucks all the negative electrons toward itself, leaving the hydrogens relatively kind of positive-ish. So all these negative electrons over here by the oxygen leaves that side somewhat negative, leaving the hydrogen somewhat positive. It's kind of like taking the covers, right? If you think of the electron cloud as covers, oxygen sort of steals the covers from hydrogens, leaving it kind of cold, and then oxygen is all nice and warm and toasty under there. Okay, so that is what we refer to that molecule as polar. It has a pole, negative pole and a positive pole. Okay. Now oxygen is nonpolar. Why? Because they're the same thing. Their electronegativities are exactly the same. It's like a stalemate in tug of war. So there's nobody. The electrons don't go to any one side. It's not like a lopsidedness to it, okay? Because they both have the same attractiveness toward electrons. Now, what this does then is it basically creates the fundamental building blocks that we need in order to start talking about probably the most important molecule in all of life, which is water itself. Now, we're mostly made out of water. Your blood plasma alone is like about 90 some odd% water, depending on your hydration levels. Overall, your body weight is about almost 2/3 to 3/4 water. And not only that, but whenever you're frustrated and you're trying to manage your body weight and you drink a bunch of water and you get on the scale and you're frustrated because you're heavier than you want to be, just remember, if you just tanked up on water, a lot of that's water weight, and water is heavy, right? So remember that your actual body weight is a lot of water. So a lot of your so a lot of your body weight can fluctuate wildly with water. So a lot of people will do that. They'll be like, wait a minute, how can I be like 3 pounds heavier than I was earlier? It's like, well, if you drink a bunch of water, that'll do it, right? And it'll actually add pounds to the scale. So it's not like you just gained a bunch of weight. That's not possible within a few hours. If you see weight fluctuations within, say, for instance, a day or within just a few hours, it's probably water weight is what's going on. Okay. So water, the reason why I wanted to sort of back up and sort of talk a little bit about polarity idea is because water is polar. That is to say that more electrons are hanging around oxygen than around the hydrogens. And so as a result, what we end up getting is something that looks like this. We get a relative negative kind of an atmosphere around the oxygen and relative positive around the hydrogens. So it's a polar molecule. And as a result, that polarity leads to a really, really important thing that water does, which is forming hydrogen bonds. Now, hydrogen bonds are basically the electrostatic attraction, typically between the positive hydrogen of one molecule and that slightly negative oxygen or nitrogen in some cases of another. So for instance, if you were to take a look at water, then you know that the charge differential is going to be positive around the hydrogen, negative around the oxygen. But if it comes in close contact with an adjacent water, then you'll see that it'll form an electrostatic attraction, sound effects not included, but this is a hydrogen bond right there. That's your hydrogen bond. So it's an electrostatic attraction between that positive hydrogen and that negative oxygen. For the most part, they're relatively weak bonds. Not like a covalent bond, not to be confused with a covalent bond, right? This is not holding two atoms together. This is simply just an interaction between two separate molecules, and it's weak. Covalent bonds are tough and hard. They're going to be difficult to break without a lot of energy. In hydrogen bonds, they're kind of like, well, sticking a balloon to your head. How many of you guys have ever stuck a balloon to your head? Take a balloon, rub it on your head, right? And you let it go. It just kind of hangs out there. And it's like fun for about an hour, depending how old you are. Right, but what happens? The balloon just stays there, doesn't it? But is it actually linked to your skull? If I tell you to take the balloon off, can you? Quite easily, right? It's just sitting there. You just take it off and there it is. Okay, done. Why? Because those are the same sorts of bonds that you have here with hydrogen bonds. An electrostatic attraction between two positive and negative sources, right? In this case, you rub the balloon on your head because the idea is you're getting one to build up electrons and the other is losing electrons. So you have basically this kind of positive negative interaction. And that positive negative interaction just kind of like hangs on to the balloon. It's like an electrostatic attraction, but it's weak. So you can easily just take the balloon off. Same thing as here. The hydrogen bonds are weak, so you can easily break them. So it sounds like a bad idea, but the important thing is remember is that they're strong in numbers. So if you have one or two hydrogen bonds, they're going to be weak. But if you have millions of them, they're going to be quite strong. A good example is a gecko. How many of you guys have had geckos? Love geckos. But you watch them kind of walk on the side of the terrarium, right? A gecko, basically, the reason why a gecko doesn't fall off the terrarium wall is because it's using hydrogen bonds to actually tether its feet to the glass. And so even one hydrogen bond is not enough to hold the gecko's weight, but millions and millions of hydrogen bonds on its feet is enough in numbers, strong, to hold up the weight of the gecko. Okay, So that's an example of the importance of hydrogen bonds. The other thing that's also important with hydrogen bonds is this is how water is actually structured. So if you were to take a look at just liquid water, what you're going to have is a bunch of water molecules that are basically kind of held together in this sort of this net-like structure of water molecules held together with hydrogen bonds. For instance, you'll see all these little dotted lines of the hydrogen bonds, and they're all basically interacting the negative oxygens with the positive hydrogens. And so you can see that they're basically all kind of interconnected with each other in this, what is a glass of water. And that's part of why water sticks together. Why when you pour it out, it flows. It's like it largely stays together as a column. Or how about this one? You've probably all seen this one. Everybody seen a video of an astronaut playing around with a little drop of water in space? Right, it's kind of like just sort of bubbling around there. It's like you just kind of like, you know, it's like a perfect little sphere, isn't it? Why? Because that's water that's connected to itself with hydrogen bonds. That's just kind of all interconnected. And so that kind of forms a structure of water. It also happens to form the properties of water. Now, the properties of water are really important because other than just being physical properties of water, they also basically lay down important biological realities that allows life to exist on this planet. Let's start off with the energetic ones first of all. Number one is with water, we're usually looking for liquid water as sort of like the evidence of life, or the liquid, the elixir of life, as we oftentimes call it. But the first thing we want to take a look at is heat capacity. Now, water has a high heat capacity, or sometimes we'll refer to it as specific heat. Now, this is kind of a chemistry thing, so just kind of follow me here. It's a thermodynamic idea. Basically, specific heat or heat capacity is defined by the unit a calorie. Notice it's capital C, which is 1,000 little c's. So basically the calorie is essentially defined as the amount of heat required to raise 1 gram of, in this case, water, 1 degree Celsius. Yeah. So a calorie you eat is a little bit different than the calories that you measure in chemistry under thermodynamics. It's actually worse. A calorie that you eat is actually 1 kilocalorie, or 1,000 calories. So typically in chemistry, you measure small c calories. And so 1,000 calories is a kilocalorie. And 1 kilocalorie is a capital C, or nutritional calorie. So in reality, you're actually getting 1,000 times more calories than you think. Nutrition. So like if you were trying to like go like chemical on it and try to break down the number of, like go do some chemistry on it, like oh, how many calories am I actually eating? You would actually have to multiply that number by 1,000. Make sense? I don't know why they did that. It's just the way things are. But just remember that next time you chomp down on your favorite sweet, which is your other instinctual craving, salt and sugar. So now what does that mean then? So first of all, here's what this means. So I want to give you an example of the difference, like a heat capacity, sort of like illustrating differences in heat capacity between different substances and how they're important. So what I want to do is I want to basically have you go out to a hot desert during a really good hot day, right? Nowhere here in Denver or Colorado for that matter, right? Go to somewhere that like is notorious for killing people, like Mojave or Death Valley, right? Where it gets up to like 150 degrees during the day. And then what I want you to do is I want you to put a shovel out there, just let it lay there. Leave it there for the majority of the day. And right around the apex of the heat of the day, around like 3-ish, 4-ish o'clock or so, I want you to go out there and I want you to pick up the shovel. What part of the shovel do you pick up? Do you grab? The wood or the plastic, right? The handle, right? Depending on whatever it's made. How come none of you guys want to grab the spade? Yeah, right? I mean, what would that feel like to you? Yeah, it'd be very hot. But by the way, it doesn't get that hot here in Denver. But heat like that, you would probably generate enough heat in that spade to where you'd probably need to go to the hospital for burns. You know the old adage, frying eggs on the street? When I was living in Sacramento, it got up to, 100-ish or so, like between 106 and 112, pretty routinely. I actually did this. I actually fried eggs on the street. It does happen. It does get hot enough. The asphalt was hot enough to actually fry an egg. So we're talking about incredible amounts of heat. So what's the difference there? They're made out of two different materials that have vastly different heat capacity. So what is heat capacity? It's the ability of a substance to absorb heat energy without changing temperature. So the reason why we make handles out of things like wood and plastic is because they have a very high heat capacity. They have the high ability to absorb lots of energy without changing temperature. Now, the reason why I did the shovel is because you have two materials that are basically connected to each other right in the same place. You can't argue that that spade got more sunlight than the handle, right? They were one and the same. They got the same amount of energy. But the difference is heat capacity. The handle had a higher heat capacity, so you could touch it without burning. The metal, however, has a very low heat capacity. As soon as it absorbs that heat, it raises that temperature. So it goes up immediately. Which, by the way, if you think about it, is the reason why we love metals, isn't it? Like, do you cook in a wooden skillet? Why not? You're like, well, I never thought about that before. Because they don't sell them. Why wouldn't they sell them? What do we need a skillet to do? You chefs who are really particular about your skillets. What if, like, for you, a quality skillet has to do what for you? Has to hold heat. It also has to do what with the heat? Has to distribute it evenly, right? Because you don't want cold spots and hot spots. That's in cooking 101, that's like when your utensils, that's one of the things you're looking for as a chef, is like this particular thing has to be able to distribute the heat evenly so that you can have even temperatures all the way throughout. But what are all of our skillets and pans made of? Metal. Why? Because they have a low heat capacity. They change quickly when they absorb heat, which is exactly what we want them to do, so that we can cook with them. Now, water has a very high heat capacity, one of the higher ones. Now, what does this do for us? Okay, I apologize for what I'm about to do to you, but I'm going to do it anyway. All right, I'm about ready to go California on you. What does that mean? Geography lesson in California. Okay, so here's what it looks like. Okay, is that good enough? Did I pass my California geography test? Not yet, because here's what I want to do. What major city is sitting right in there? Yeah, it's LA, LA Basin, right? What are the temperatures like in LA? Ooh, nothing close to that. No, LA's not that hot. Nobody would live there if it were. Considerably cooler than that, actually. Probably 80s on average, give or take, right? 105 would be considered a real hot spike, right? That'd be its extreme. How about right up here? What major city is sitting right around there? I left my heart in. Notice how nobody left their heart in LA. You leave your heart in San Francisco, which actually I hate San Francisco, but it's because I grew up in the Bay Area. But what are the temperatures like in San Francisco? Like year round? 60s, give or take a few degrees, all year round. If it gets up into the 80s in San Francisco, people are coming apart at the seams. It's very cool. It's like light windbreaker weather, like all the time in the Bay Area. It's very cool. Now let's go ahead and from LA, let's start moving inland. As I start to move inland, what am I finding like right in this area of California? Yeah, deserts, right? So you're starting to get those deserts in Arizona is like right here, right? You're starting to get those deserts, the Sonoran Desert that Mojave, Death Valley, those are all deserts that kind of are in southeastern California, and they kind of cross over the border to Arizona, right? So those aren't very far away. A couple hours, boom, you're there, depending, of course, on traffic, right? From San Francisco, you go about maybe, I would say, hour, not more than an hour and a half inland. Which major city do you hit right here? Yeah, the state capital, right? Sacramento. You know what a lot of people don't realize is in this area of California, which is the Central Valley, it gets really hot. A lot of people don't realize that. Really, really hot. Like routinely, it's over 100 degrees pretty much all summer long. In California, it's great. I mean, Sacramento, it's great because it cools off. Because you get the Sacramento River, the Delta breeze comes in there, kind of cools you off in the evening. And so it's livable. Up here in the northern end, before you hit the Cascades, God help you. Because it gets hot and it cools down to like maybe the upper 80s, like overnight. And then it'll heat up to like the teens, 100 teens. And it'll stay hot because there's nowhere for that heat to go. So the valley is incredibly hot. This is where I fried the eggs, was in Sacramento. Okay. A lot of people don't realize that. Southern Valley, same thing. Bakersfield, Merced, Fresno, those can also be hot. Southern Valley is also hot. But you only were like maybe an hour and a half at most. And if you keep going, you're going to get foothills. Sierra Nevada is going to be right here. Now you're in boreal territory. But all along the coast right here is cool coastal mountains. Lots of rain. Very lush and green. So here's the question. How come there's such disparity between temperatures? How come San Francisco is so like pleasant? And then just a very short drive inland. We're not talking about driving an entire state. We're talking about maybe an hour and a half at most. That's with traffic, heavy traffic. You're already into like 100 degrees. Actually, the 100 degrees starts before that, to be quite honest with you. It starts only like probably maybe about 30 to about 40 minutes into your drive, and you're already at the 100. How come there's such a disparity in temperatures? Cool coasts, hot inland. But what? Yeah, because you got this gigantic heat sink out here. Water, the Pacific Ocean, that absorbs all that solar radiation without changing temperature, and it keeps those northern coasts cool, and the southern coasts too. But guess what? As you go inland, you get away from the ocean effect, and there's no more heat sink soaking up that solar radiation. Temperatures start to go up, they start to increase, and the internal part of the state gets very, very hot. Hot enough to where during the summer, for the most part, your strategy all summer long is just going from one air-conditioned place to another. It gets like really, really hot. Nothing in Denver is anywhere close to what that was like. That was the only place where I almost actually passed out. Of course, I was dumb. Actually, we used to have that all the time in California. In the grocery stores, they actually had like a crash cart in the entryway of the grocery store. And they had like, it was kind of quasi-security medical person was always kind of somewhere in that area, because it commonly happened all the time, because my brother was a grocery clerk, and so he saw it all the time. It'd be like 106, 107 outside, and somebody would come in and you'd run into that 65-degree air-conditioned store, and it's you just they go, they're boom, they're gone. And then you have to grab the crash cart, and then it was nothing. People just step over them and like, okay, just out of the way, because it happened all the time. It happened so often that we're just like, okay, that's just the way it is, and that's a real thing. So you kind of had to sort of like regulate yourself. And when I passed out, that wasn't what happened. I was stupid. I was a teenager in high school on the tennis team, and I played my doubles partner. We played tennis, and it was like 106. So we played, and we always like went after each other. I mean, it was like, it wasn't just like, oh, let's have fun. We were just like, okay, I'm better than you. And because we were fighting in singles, we were also like number 5 and number 6. So we were trying to like get that next spot. Like I was trying to displace him so I could be number 5, and he was at number 5. So we were constantly at each other. And yeah, that one was one where I started getting a little on the dizzy side. I remember that. I'm like, I gotta sort of sit down because it's not going to go well. So I got to slow down here. It's a real deal. Heat exhaustion is a problem, and especially very, very hot areas. So the other one that we're going to be taking a look at, and I want to cover the heat of vaporization, and then what we'll do is we'll hit water solvent for the next time, is the heat of vaporization basically is essentially the heat at which liquid becomes a vapor. So basically steam, right? And so what happens is the heat goes into the steam and it kind of vaporizes. And so for us, that is about 100 degrees. So it looks like this, right? So generally speaking, when you take a look at water, for the most part, between roughly 0 and 4 degrees or so, it's going to be a solid. So it's going to be ice. So that's basically when our freezing occurs at 0 degrees, right? And then kind of you have this little ramp up. It's a very steep ramp up, so you don't really have a whole lot of like layover there. But then from then until about 100 degrees, it's a liquid. And then you have your conversion to gas. So basically your gas molecules or your water molecules will sort of just peel off and just sort of dissipate into the atmosphere as gas. That's the heat of vaporization. So the reason is, what's the biological significance of that? Well, let me take just kind of example. I'm not going to have you guys just sort of think your way through this. I'm just going to throw it out there just to illustrate this. We're mostly made out of water, which basically means that we can absorb a lot of energy before we vaporize. That's a good thing. Vaporization is a bad idea, especially if you're trying to do chemistry. Reactant A needs to have contact with reactant B. You can't do that if they're separated by lots of space in a gas. Okay, so you simply can't do fundamental chemistry unless you have all of this together in one sort of watery matrix. The other thing is this. Imagine you were made out of acetone instead of water. Where would you get acetone? If I told you to come back with some acetone, what would you come back with? You manicurist, you. Yeah, nail polish remover, right? And so when you take a look at acetone, one of the natures of acetone is it's very what's called volatile, right? It evaporates very quickly, very easy. Pour a little bit on the table, it's gone, like in no time. If we were made out of acetone, at room temperature, we would be a gas cloud, which would not be conducive to life, would it? Because it has a very low heat of vaporization. Since we have a very high heat of vaporization, what that means is we can take on and absorb a lot of heat energy before we evaporate. That basically means on a good hot day, we can go out there like at 106 degrees and play tennis without evaporating. That's biologically necessary, right? So that kind of lays some of the groundwork, the foundation for just being a chemically competent structure. That's what we need to be. You can't be that if you're just evaporating everywhere. Okay, so that's the reason why heat of vaporization is important. So what I'm going to do is I'm not going to rush my way through this chapter, because when you take a look at biology, these are some of the most important concepts that we're in right now. Okay, especially with water. And so some chapters I'll speed through, I'll cut and abbreviate, and others I will not. This one I will not, okay, because this is a really, really important one. So we're going to start off with the next property of water, which is the solvent properties of water, and we'll do that one on Wednesday.